have this box that's going to slide down this incline, and we're supposed to find the acceleration. They give you the angle theta, and they give you mu sub k. So the first thing we're going to do is draw a free body diagram. So here's the box. Its mg goes straight down. It has a normal force that's perpendicular to the surface, so that goes this way, normal force. And then the friction is going to be parallel to the surface and opposite to the motion. So since it's going to slide down the hill, the friction goes up the hill. So there is our free body diagram. Next, we're going to bring in our axes, and it's always a smart idea to put the y-axis on top of the normal force. So there's my y-axis, and then the x-axis this way, perpendicular to that. So I see that my normal force is flat on the y-axis, and the friction force is flat on the x-axis. It's just this mg that's slantways. So since that's slantways, I need the angle between mg and the x-axis here. So that's this angle here, which I recognize as being that angle up there. So the angle I'm going to use in there is going to be 90 minus theta. Now I'm writing 90 minus theta, but you actually use your theta, subtract it from 90, and write that instead. Alright, so now I'm ready to write the equations. In the x direction, on the x-axis I have the friction force, but it's to the left. If you tip your head to the side, that's to the left. So that's minus F. And then the x component of mg is going to be to the right, so that's plus mg cosine, because it's the x equation, we always use cosine, and then the angle that we're using is, I'm going to write 90 minus theta, but you just write your angle that you figured out just a minute ago. So that's the left-hand side of my x equation. This is going to be equal to ma, because it's accelerating down the hill. Now the y equation. Flat on the y-axis we have the normal force, n, and then the mg force is pointing downward in the y direction, so I'm going to write mg sine 90 minus theta. I'm having a heck of a time with this pen. And this is going to be equal to 0 because it's not moving at all in the y direction. Now, we're working with friction, so we can write down the friction force. In this case, it's mu sub k times the normal force, because it is sliding, so I can use the equation, and I'm using the sliding coefficient. So I'm going to put this all together. I'm trying to find A. So I have these three equations. I just plug them into each other. Wish me luck with this pen that's not working for me. But I start with this top equation, the x equation, because it has A in it. And starting from the left-hand side, the first thing I notice that I don't know what it is F. So I'm going to use this equation here, F equals mu sub k n, and plug that in instead of F. So minus mu sub k n plus mg cosine 90 minus theta equals ma. And this is good because I know mu sub k, but I don't know the normal force. Oops. So let's go back and look. This equation here, the y equation, has the normal force in it. This equation tells me that the normal force is equal to mg sine 90 minus theta. So I'm going to plug that in instead of normal force. Minus mu sub k mg sine 90 minus theta plus mg cosine 90 minus theta equals ma. Phew! So I have everything in this equation except A. I can divide everything by m because I know that's not 0, that's okay. So I can get rid of those m's. And I'll find out that the acceleration is equal to g cosine 90 minus theta minus mu g sine 90 minus theta. And I can plug in and calculate that. That would be part A. For part B, they want you to find the final velocity. You now know the acceleration, and we have v squared equals v naught squared plus 2a x minus x naught. In the problem, they gave you x minus x naught. That's the distance down the hill. We know that v naught is equal to 0. We have the acceleration. We just calculated it, so we can find this final velocity.